Beyond the luminous spiral arms of our galaxy, in the freezing expanse of the interstellar void, an invisible phenomenon drifts in absolute silence. We are accustomed to thinking of the cosmos as a tapestry of brilliant stars and glowing nebulae, bound together by the immense anchoring gravity of galactic cores. But the universe harbors anomalies that defy this orderly structure. Plunging through the dark entirely untethered from any star system are rogue black holes. These are not the stationary, supermassive giants sitting at the center of galaxies, but nomadic remnants of ancient stars, wandering alone through the endless night. To understand the profound isolation of these objects, we must first strip away our comforting illusions of a static universe. A rogue black hole emits no light, reflects no radiation, and offers no warning of its approach. It is a pure sphere of gravitational influence, bounded by an event horizon from which nothing, not even a photon, can escape. Without a companion star to strip matter from, there is no glowing accretion disk to signal its presence. It is a perfect, silent ghost, moving through the galaxy at millions of miles per hour, completely cloaked in darkness. How does an object of such terrifying power become unmoored from the cosmic fabric? The answer lies in the violent and chaotic deaths of massive stars. When a giant star exhausts its nuclear fuel, its core collapses under its own immense weight, triggering an explosion of unimaginable fury. During these catastrophic detonations, the collapsing core can sometimes warp and buckle unevenly. This asymmetry is the birthplace of the wanderer. If the star explodes with greater force on one side, the newly formed black hole acts like a cosmic cannonball. These violent ejections are known among astrophysicists as supernova kicks. The sheer kinetic energy transferred to the collapsed core is staggering, often enough to sever the gravitational bonds tying it to its native star cluster. Propelled by this explosive thrust, the black hole begins its long solitary journey, shooting out into the sparse, cold regions of space. The realization that these stellar corpses could be forcefully evicted fundamentally changed our understanding of stellar dynamics. We once believed that what was born in a cluster stayed in a cluster, yet the existence of these untethered masses reveals a universe defined by violent ejections and shattered gravitational bindings. The black hole's immense pull continues to warp space-time as it travels, but it is no longer part of a system. It is a solitary agent of gravity, unbound and unpredictable, but the death of a single star is not the only mechanism capable of launching these dark leviathans. On a much grander scale, the architecture of the universe is shaped by galaxy mergers. When two massive galaxies collide, their central supermassive black holes inevitably sink toward the new center of the merging system. As they spiral inward, they form a binary pair, a destructive waltz of unfathomable mass and energy. If a third supermassive black hole enters this volatile arena, perhaps from a subsequent galactic collision, the gravitational dynamics become wildly unstable. The complex interplay of three immense bodies cannot last. In a breathtaking display of celestial mechanics, the system will violently expel the lightest of the three. These events, known as gravitational slingshots, transfer an immense amount of orbital energy to the ejected black hole, hurling it outward with terrifying velocity. The scale of this ejection defies human comprehension. The expelled supermassive black hole, containing the mass of millions of suns, is accelerated to speeds exceeding 3 million miles per hour. It tears through the interstellar medium, ripping past star systems and nebulae until it breaches the outer limits of its host galaxy. It escapes into the intergalactic void, a rogue titan condemned to wander the unimaginable distances between galaxies for the rest of time. This brings us to one of the greatest challenges in modern astrophysics. If these nomadic objects emit no light, possess no glowing disks, and travel through the darkest reaches of the cosmos, how do scientists find them? Hunting for an invisible object against the black canvas of the universe seems like an impossible task. We cannot look for the object itself. Instead, we must look for the subtle, ghostly footprints it leaves upon the light of other stars. The key to unmasking these hidden wanderers lies in Albert Einstein's theory of general relativity. Einstein proposed that massive objects do not merely pull on things, they actually curve the fabric of space-time around them. When light from a distant background star travels toward Earth, it must follow the curvature of space. If an invisible mass like a rogue black hole passes directly between our telescopes and that distant star, the black hole's gravity acts as a colossal magnifying glass. This extraordinary optical illusion is called gravitational microlensing. As the rogue black hole drifts across the line of sight, it bends and focuses the light of the background star, causing the star to appear temporarily and dramatically brighter. The invisible mass does not block the starlight, it gathers it, magnifies it, and redirects it toward Earth. It is a fleeting alignment, a cosmic coincidence that offers a brief, brilliant window into the unseen. The signature of gravitational microlensing is highly distinct. Unlike a star that pulses or flares due to its own internal mechanisms, a microlensing event produces a smooth, perfectly symmetric curve of brightening and dimming. Furthermore, the magnification affects all colors of light equally. If a star brightens in this exact mathematical pattern without changing its color, astronomers know they are not witnessing a stellar eruption. They are watching a phantom mass passing in the dark. Searching for these microlensing events requires monumental patience and technological precision because the alignment must be nearly perfect. These events are incredibly rare. Scientists must continuously monitor millions of stars in the dense central bulge of the Milky Way, night after night, year after year, hoping to catch a single telltale flash of magnification. It is a testament to human ingenuity that we can find an invisible needle in a cosmic haystack by watching how the needle bends the light around it. When researchers finally isolated the first definitive candidates for rogue black holes, the implications rippled through the scientific community. The data suggested that these solitary wanderers are not mere anomalies, but a fundamental component of our galaxy's population. Statistical models extrapolated from these rare events indicate there could be anywhere from 10 million to 1 billion rogue black holes drifting through the Milky Way alone. We are sharing our galactic neighborhood with an invisible armada. The discovery of this vast, unseen population inevitably drew the attention of cosmologists grappling with another profound mystery: dark matter. For decades, scientists have known that galaxies contain far more mass than we can see. The visible stars and gas only account for a fraction of the gravitational glue holding galaxies together. Could this sprawling network of rogue black holes, completely dark and incredibly massive, be the missing mass we have been searching for? While the idea is tantalizing, current astrophysics suggests that rogue black holes, though numerous, cannot account for the entirety of dark matter. The sheer volume of missing mass required to bind the universe together is too vast to be explained solely by stellar remnants. Dark matter is widely theorized to be composed of undiscovered subatomic particles rather than collapsed stars. Yet these wandering black holes represent a crucial piece of the puzzle, a significant reservoir of hidden mass that complicates our maps of the cosmos. Understanding the distribution of these nomadic objects offers profound insights into the evolution of the universe. Every rogue black hole is a fossil, carrying the history of a violent supernova or a catastrophic galaxy merger from eons past, stretching back through the 13.8 billion years of cosmic history. By tracking their movements and estimating their numbers, we can reconstruct the chaotic youth of our galaxy. They are the scattered debris of cosmic construction, revealing a universe that is far more turbulent and dynamic than the peaceful night sky suggests. It is natural to wonder what would happen if one of these invisible wanderers drifted into our own solar system. While the probability is infinitesimally small, the scenario is a fascinating exercise in gravitational physics. Long before it reached the Sun, its immense mass would begin to perturb the orbits of the outermost comets in the Oort cloud, sending a shower of icy bodies plunging toward the inner planets. The delicate gravitational balance of our planetary system would be permanently altered by a ghost we could not even see. As our observational tools become more sophisticated, the veil of the dark universe is slowly lifting. Next-generation space telescopes designed to survey billions of stars with unprecedented precision will inevitably detect thousands of new microlensing events. We stand on the precipice of a new era in astronomy where we will map the invisible geography of our galaxy. What other unseen leviathans are waiting to be discovered in the spaces between the stars? The existence of rogue black holes reminds us that the universe is not a static museum of shining stars, but a wild, untamed frontier. They challenge our perception of reality, forcing us to acknowledge that some of the most powerful forces in nature are completely hidden from our eyes. As we continue to search the darkness, we do not just find dead stars, we uncover the profound, hidden majesty of a cosmos that is forever in motion, beautifully complex and endlessly mysterious.